5.1 is the beginning of a topic called integration. And what integration does is it's the opposite of a derivative. They actually call it the antiderivative. And what you do is you find the function whose derivative is what you're looking at. But before we get into that, we have to talk about what an integral really is. And what an integral really is the area underneath a graph. So to begin, we're going to talk about Riemann sums, which are ways that you can draw little rectangles and add the areas together to approximate the area under the graph. And this is a way that we can approximate what an integral will be. And in Calculus 2, they take this a step further and talk about different approximations that you can have. There's a trapezoidal approximation and the Simpson's approximation. So this is the first step, which helps to explain the integral. So the Riemann sum is drawing rectangles and adding the areas together to approximate the area under the curve. The more rectangles you use, the better the approximation, and it's because the error is smaller. Here's a left and right Riemann sum. The right Riemann sum is on the left, and the left Riemann sum is on the right. That wasn't planned very well. But in either case, notice a right Riemann sum, the right endpoints of the rectangles are what touch the graph. If the graph is increasing, the right Riemann sum will be an overestimate, because see, there's more area in the rectangles than there is in the graph. If the graph is decreasing, the right Riemann sum gives you an underestimate, because of the way you draw the rectangles. With the left Riemann sum, the left-hand side of the rectangle is what touches the graph. If the graph is increasing, like this example, it's an under-approximation, because there's less area in the rectangles as there is in the graph. If it's decreasing, it will be an over-approximation because of the way you draw the rectangles. And notice, if I add the areas to these rectangles, it gives me a guess as to the area under that curve. The more rectangles, the smaller there's going to be an error in there. And so that's really what this section is about, is drawing these rectangles and adding their areas. And they tell you how many rectangles to draw, and you can decide where you want your Riemann sum to be. So one of the topics that we do Riemann sums with is velocity and displacement. So remember from earlier that if we know the position, then to find the velocity we take the derivative of the position. So what if I'm giving you the velocity graph instead? So if you take the derivative of position to get velocity, then if I give you velocity, I have to do the antiderivative to get position back. I have to take the derivative away to get back up to position. And so the area under the graph of a velocity function gives the displacement of an object. And to think about displacement, you should think about the paycheck you get. When you get a paycheck, there's a gross pay and a net pay. And the gross pay is how much you earned. That's kind of like distance. It's how far you actually move. Then there's the net pay, which is what happens after you take out taxes. You can think of the displacement kind of as a net distance. So let me show you what I mean. In this example, it says, Matt walks 3 miles east, then turns around and walks 1 mile west. So I drew a little picture. He starts here, and he walks to the east 3 miles. Then he turns around and walks back west, or he walks to the east 3 miles, turns around and walks west 1 mile. You say, well, how far did Matt walk? That's the distance. And if you look, Matt walked 3 miles plus 1 mile back for a total of 4 miles. But the displacement is how far he actually moved from his original spot. He only moved 2 miles from his original spot, so the displacement is 2 miles. That's how much the place has been moved. But the distance is 4 miles because that's how many miles he actually walked to get there. So here's an example of approximating a displacement. When we use the displacement, anything that's above the x-axis is positive. That's like moving to the right here, 3 miles. Anything below the x-axis is negative. That's like moving left 1 mile. So when we're dealing with displacement in graphs, we draw the graph and plot the rectangles. And any area that's above the x-axis is positive, and any area below the x-axis is negative. So here's an example of approximating displacement. They give me a velocity function. And they say the velocity is 1/2 t squared plus 4, and t goes from 0 to 12. And they want you to approximate the displacement for 4 rectangles. So what I'm going to do is I'm going to sketch a graph of this thing. And when I look at the graph of this, and I'll draw it on the calculator here, it's going to look something like this. And I'm going to put in 12 for t. And that takes me to 76. Now here's the graph for the velocity, which is 1/2 t squared plus 4. And I go from 0 to 12. Make it match up. So all I did was use my calculator, or my brain, to sketch a graph of what this looks like. And notice all of the area is above the x-axis. So when I find these areas, they're all going to be positive because the area is above the x-axis. And notice I want 4 rectangles. And I want them all to be the same width. Well, notice I have 12 to work with. There's a space of 12 on the x-axis. And I want to fit 4 rectangles in there. So if I divide those numbers, I know that each rectangle has to have a width of 3. And I'm going to use the right endpoint, but you could have used the left endpoint. 1, 2, 3, 4. Those are my 4 rectangles. And I know each rectangle is 3 wide, so that's 3, 6, 9, and that's 12. So notice I chose to use the right Riemann sum, but you could also use the left Riemann sum. If you use the left Riemann sum, it would be an underestimate. The right Riemann sum is an overestimate. So I figured out that I had 12 spaces to work with on the x-axis, and 4 rectangles means each rectangle has a width of 3. So now I have my rectangles drawn. To approximate the displacement, I just find the area of each one and add it together. That will be an approximation of the displacement. Since all of the area is above the x-axis, it will be positive. Well, let's look at the rectangles. The area of the first rectangle. The width is 3, and to find the height, I have to figure out how tall this thing is. Well, to figure out the y value here, notice it touches the graph there, which is 1/2 t squared plus 4. So to find the height of the first rectangle, I take 3 and plug it in to the velocity function. Because it's touching the graph there, that's how tall the rectangle is. So I get 1/2 times 3 squared plus 4, and that gives me 8.5. So the height of the first rectangle is 8.5. That's what that thing is. It's 8.5 tall. If I put 8.5 in here, 8.5 times 3 gives me 25.5. Then I do the second rectangle. The width is 3. To figure out the height, I figure out where it touches the graph when t is 6. So the second height is 1/2 6 squared plus 4. That gives me 22. So this graph here is 22 tall. So my height is 22. The height is 22, the width is 3, the area is 66. So the first area is 25.5. The second area is 66. It's both above the x-axis, so they're both considered positive. The third area, width is 3. I just need to find the height. And to find the height, I plug 9 into the function. So I get 1/2 9 squared plus 4. And that gives me 44.5. That's how tall that is. So the height is 44.5. The width is 3. So the total area is 133.5. The last one happens where the graph hits 12. So the width of all these rectangles is 3. To find the height, I plug 12 in, because that's the x value that this is occurring at. When I plug 12 in, I get 76 out. And I multiply that by 3 because that's the width. and I get 228. So this last rectangle has an area of 228. So to find the total area, I just add all of these areas together. When I add them all together, I get the approximation of the area of I get the area of the rectangles, which approximates the area under the curve. So the total area, all of these are positive since they're all above the x-axis. I add them together to get the displacement. By the way, if you'd used a left Riemann sum, you'd have gotten a smaller number, which would have been an underestimate. It would have been valid, though. It just would have been a smaller approximation. When I add these areas all together, I get 453. So that's my approximate displacement, which is really the area under that graph. Well, the approximation of the area under that graph. The actual area will be smaller than that number because I've been over-approximating with my right Riemann sum. A left Riemann sum would have under-approximated. So that's the total area there. You're just finding the area of the rectangles. And notice they tell you how many rectangles to draw, and they tell you where to draw them. So to fit them in with the same width, you take the interval and divide it by the number of rectangles. A lot of times you'll see this as b minus a over n, where n is the number of rectangles, b is the second endpoint, and a is the first endpoint. 453. We can do this in general. This one wants us to calculate the left and right Riemann sums to the cosine of x with 4 rectangles from 0 to pi half. So this could be a displacement if that cosine of x were a velocity, but they just like us to do this in general. So what I'm going to do is I'm going to draw the graph. I'm going to do it twice. First I'm going to use the left Riemann sum. So we'll do that one first. Now here's a picture of the cosine of x. I should probably do it in a darker shade. Yeah, at 0 the cosine is 1, and at pi over 2 the cosine is 0. So there is the graph of the cosine of x from 0 to pi over 2. And it says that I want to draw 4 rectangles to do this. And this is a left Riemann sum. So first I want the left end of my rectangle to touch the graph. Now how wide is each rectangle? Well, pi over 2 is how far I have to fit them. And I want to fit 4 rectangles inside pi over 2. So when I divide these, you can think of that as 4 over 1. This is pi over 2 times the reciprocal 1/4, which is pi over 8. So my endpoint is pi over 8, 2 pi over 8, 3 pi over 8, and 4 pi over 8 is pi over 2. So we got pi over 8, 2 pi over 8, I'll write them in here. 2 pi over 8 is pi over 4, 3 pi over 8, and 4 pi over 8 gives me pi over 2. So I'm going to draw it so the left endpoint is what's touching my graph. Notice my 4 rectangles, and the left endpoint is what's touching the graph on those 4 rectangles. Since the cosine of x is decreasing here, it's going to be an overestimate, the left-hand Riemann sum. So all I got to do is find the area of each one of those rectangles. The widths are pi over 8. So to find the first area, I need to find the heights. Now this first point touches the graph at 0. And so the height of the first rectangle, h1, is what I get when I plug 0 into the cosine of x, which is 1. The height of the second rectangle is where pi over 8 gets plugged in to the cosine of x. Now if you're typing this into your calculator, make sure that you're in radian mode. But pi over 8 is 0.924. Gotta be in radians for this to make sense. The height of the third rectangle, notice the third rectangle is where pi over 4 touches the graph. That's how tall it is. So this is the cosine of pi over 4. That's a reference angle that I happen to remember. So it's root 2 over 2. But if you type it into your calculator will actually tell you that it's 0.707. The height of the last rectangle, using the left Riemann sum, is where 3 pi over 8 touches cosine of x. Again, that's not a reference angle, so you can't necessarily just tell you what the answer is. But I use my calculator in radian mode. Cosine of 3 pi over 8 is 0.383. So I know the height of all these rectangles, and the width is pi over 8. So the area of, notice they're all above the x-axis, so all these areas are positive. If the area is below the x-axis, it would be negative. So the area of the first rectangle, the width is pi over 8, and the height is 1. So I get pi over 8 as the area of the first one. To find the area of the second rectangle, the width is pi over 8, and the height is 0.924. So if I do pi over 8 times 0.924, that gives me 0.363. The third rectangle is pi over 8 times the height of the third rectangle. That's what happens when I hit pi over 4 in there. So I do pi over 8. This gives me 0.278. The last rectangle, area 4. We have pi over 8. And the height of that last one is 0.383. So pi over 8 times 0.383. That gives me 0.150. So the area of this rectangle is 0.15. So the total area is what I get when I add these together. Pi 8 is the area of the first, plus 0.363 is the second, plus 0.278 is the third, plus 0.150 is the fourth. So I add these together. Pi over 8 plus 0.363 plus 0.278 plus 0.15. And this gives me 1.18 as the total area under that curve. Now that's an over approximation because if you'll notice when I drew the rectangles, they were bigger than the area in the graph. So that's for the left Riemann sum. Now the problem is asking me to also do a right Riemann sum, so I will do that as well. By the way, the area under this graph turns out to be 1 when you use calculus. So if you use actually calculus to find it, which we'll do in a little while, you'll get the exact area is 1. But the over approximation is 1.18. Oh, let's try it with the right Riemann sum. Same graph, same picture. It's just our rectangles will hit in a different spot. There's the cosine of x from 0 to pi over 2. Same endpoints. The endpoints don't change. So the endpoints are pi 8ths, pi 4ths, 3 pi over 8, and pi over 2. And this time, it's a right Riemann sum. So I'm going to draw this so the right end of my graph, or the right end of my rectangle, is what touches my graph. Notice that last rectangle isn't tall at all because where the right end touches is pi over 2. And so the height is 0 there. But I have 3 rectangles, and the width of all these rectangles, just like before, is pi over 8. This is a right Riemann sum, because the right side of the rectangle is touching the graph. So I got to figure all the heights. The height of the first rectangle is where pi over 8 hits cosine of x. So that's 0.924. That's the cosine of pi over 8. Pi over 8 is where that first rectangle touches the graph. So the first height is 0.924. To find the second height, it's where pi over 4 touches the graph, which is that root 2 over 2, or 0.707 if you like decimals. The third height is where 3 pi over 8 touches the graph. And we looked before, the cosine of 3 pi over 8 gives me 0.383. The last endpoint touches at pi over 2, so the last height is the cosine of pi over 2, and that one works out to be 0, because it's the right endpoint that's touching the graph now. So I can find the area of each rectangle. The first rectangle, the width is pi over 8, and the height is 0.924. And that gives me 0.363. The second area has a width of pi over 8 and the height of 0.707. That gives me 0.278. The third area is the width is pi over 8. The height is 0.383. That gives me 0.150. I'll be right back. The last area, the width is pi over 8. The height is 0. So the last area is 0. So I can find the total area by adding these together, 0.363, 0.278, 0.150, and 0. So for the total area, which is my right-hand approximation, I get 0.791. And that's the right Riemann sum. Notice all the areas were positive because it's above the x-axis. And notice that this is smaller than the actual value because I'm missing some spaces. So this gave me an underestimate of 0.791. The overestimate was 1.18. In reality, the answer should have been 1. So that gives you an idea of how to use a left and right Riemann sum, and that will start us off in working with integrals.